Welcome to another lecture of the series of DC-DC power converters. So in this lecture, we will discuss about higher order DC-DC voltage converters, that is SEPIC and Chuck converter. In the last lecture we have seen regarding the DC-DC current converters, the buck derived, boost derived, and buck boost derived DC-DC current converters, and how to synthesize different types of current converters. Then how to transform the current converters into higher order voltage converter, where we have multiple inductances and capacitances. So fourth order DC-DC converters, we went with synthesizing the topologies of higher order or fourth order DC-DC voltage converters. So we have seen that in the last lecture and introduction to that. So in this lecture we'll see only the two popular fourth order DC-DC voltage converter, that is SEPIC and Chuck converter. So first we'll see SEPIC converter. So SEPIC converter means single-ended primary inductor converter. That is the full form of SEPIC converter. So a SEPIC converter has, in the input side, there is a DC source, then there is an inductor placed here, L1, this is V in, this is RL1, this is L1, RL1, L1, input voltage. So this is the current IL1. After this we have a switch here, S1, then we have a capacitor here, C1. This current is IC1 and this voltage is PC1. This is IS1 and this is VS1. V in and I in equals to IL1. So after this, we have a inductor in the middle leg, second inductor. So this is L2, RL2, this is IL2. Then we have a diode, D1. So this is BD1 and this is ID1. After that we have a secondary capacitor, the load capacitor, C2. This is IC2 and this is V0. And then we have a load where this current is I load. So this is the converter. This is a SEPIC converter. So here we have two inductors and two capacitors. So here, so in the previous converters, we used to analyze, or we used to start drawing the steady state waveform of these converters with respect to only one inductor current. But here we have two inductors, IL1 and IL2. So here we have two states of analysis, that is IL1 and IL2. And here what happens is that when S1 is on, at that time D1 is off, and when S1 is off, D1 is on. So when S1 is on, the circuit looks like, so here I'll ignore the ESR or equivalent series resistance of the inductors. This is open, and then here we have this thing. this is VL1, this is VL2. Here also this is VL2 and this is VL1. This is IS1. IC2 iload. So this is the steady state equivalent circuit of the SEPIC converter when the switch is on, and when the switch is off, when S1 is off, the circuit looks like this is open. This is the capacitor C1. This is the inductor. Now this is short circuited. So here I'll draw like this. The diode is forward biased. iLoad, ID1, here VD1, here this is VD1 and ID1 is 0. So whatever is 0 I'm not mentioning it here. So here, okay, yeah, ID1, L2, IL2, VL2, C1, VC1, IC1. Here IS1 is 0. So here we have VS1, here this is L1, this is IL1, VL1 plus minus, and this is Vin. Okay. So instead of drawing the waveform of all, so yeah, we'll draw the waveform of all all the states and all this other things of the converter. So in order to we start the analysis of the converter. So for that we'll draw this thing. So first we'll draw the switching pulses. Say that these are the switching pulses. Switching pulses S1. This is time t. Okay. There will be a lot of waveforms, so on one graph we'll draw multiple waveforms to save our space, and also because if we superimpose one waveform on the other, we'll be able to identify the relation between the two waveforms. So that we'll be doing here, because as it has more number of states, so here the number of waveforms also will be increased. Okay, so we'll first start with the input side. So here, as I said, we have two inductors, so we'll assume that there are two triangular waveforms by assuming that the converter operates in the continuous conduction mode. So first we'll see what is the type of the converter. Is it a buck derived, boost derived, or buck boost derived, and then accordingly we'll see the transfer function, means what is the minimum load requirement and all. But as of now we'll assume that everything is in CCM, continuous conduction mode. The inductances are more than critical and the load is sufficient. R is greater than R minimum. So that's why first we'll start with VL1. So yeah, first inductor L1. So when switch is on, VL1 equals to Vin, and when switch is off, so first we'll draw on it is Vin, and when the switch is off, Vin equals to VL1 plus VC1 plus VL2, and here VL2 is what? V0. So here I haven't mentioned V0. See, this is V0 plus minus V0 minus plus, and here also, yeah, here I have mentioned V0. So yeah, in the first case VL1 is equals to V in, and in the second case VL1 equals to V in minus VC1 minus V0. So in order to have amp second balance, that waveform has to go in the negative direction, because area, positive area equals to negative area, then only the inductor current will be reaching steady state. So V in minus VC1 minus V0 should be negative, which means that VC1 plus V0 should be greater than V in. That then only the VL1, the amplitude of VL1 will be negative. So here I'll draw like this is V in. And yeah, this is V in during positive time. During negative time, V in equals, if you apply KVL in this loop, if you go in this loop like this, V in equals to VL1 plus VC1 plus VL2. Here VL2 is V0 because the diode is forward biased. So what is VL1 is V in minus VC1 minus V0. This is the expression. This waveform is of VL1. Quickly we'll draw IL1 waveform. So IL1 waveform is nothing. For if the voltage is positive, this will rise. If it is negative, the current will fall, and we'll assume that there is a steady state. So it is a triangular waveform with a constant band. So this is called as delta IL1, and it has some average value which I'll be mentioning here. This average value is called capital IL1. So this waveform, purple color waveform is IL1 waveform. Okay. So here we have two inductors. So we have to do volt second balance twice, because we have to establish the relation between V in and V0. Here, even if we do volt second balance for L1 inductor, we'll get a relation between V in and VC1 and V0. But we want to eliminate VC1. So for that we have second inductor. So for that we'll do the separate analysis. So as of now I'll mention that this area is A1 like this. And this area is A2. So this time is D into T switching, and this time is 1 minus D into T switching, off time. So first inductor is done. Second component is the switch. First the switch. When the switch is on, voltage across voltage across it is 0, and when the switch is off, voltage across it is what? VS1 is what? VC1 plus VL2 or VC1 plus V0. So 0 and VC1 plus V0, because if we have to apply KVL in this loop only, not in that loop. Or V in equals to VL1 plus VS1. Both the things. Means either VS1 is V in minus VL1, or it is VC1 plus V0. Both the things we can write. So first it is 0, and then it is this value 0 and this value. Oh. Zero, or this value. What is this value? Either it is Vc1 plus V naught or V in minus VL1. Okay, both of them. This is Vs1. Now we'll draw Is1. We'll keep the color for current same because we have to denote the current in terms of the inductor currents I11 and IL2. So when the switch is on, what is the current? IL1 is Is1 plus Ic1. When the switch is off, the current is 0. So we'll draw here 0. Switch of current is 0. You just have to see what is the current in the positive time when the switch is on. So here we can write VL1, sorry, IL1 is Is1 plus Ic1, or Ic1 equals to IL2. So Is1 plus IL2. So we can write Is1 as IL1 minus IL2. So this is the value of the current. So I think instead of drawing the waveform of this thing, first we'll draw the waveform of the second inductor first, and then we'll draw the switch. So if I like this, I will bring it here. Yeah. So first we'll draw the waveform of the second inductor. First the VL2. In first case, what is VL2? VL2 equals to minus Vc1. Here VL2 equals to minus Vc1 because switch 1 is shorting it. So we'll assume that Vc1 is positive, so it is some negative value. When it is on, it is minus Vc1. Yes, this is minus Vc1. And when the switch is off, what is VL2? VL2 is V naught. VL2 is 1. We have to find a shortcut way of expressing it, this term. So Vin equals to VL1 plus Vc1 plus VL2, or VL2 is equals to V naught. So directly we'll write in terms of the states instead of writing in terms of inputs and other states. In this case, Vin equals to VL1 and Vc1 equals to VL2. And as this diode is reverse bias, so we can't express VL2 in terms of V naught. So VL2 is minus Vc1, only this we can express. So VL2 is V naught plus V naught. So this is V naught. This is waveform of VL2. Now we'll draw IL2. So for IL2 we'll use the other blue color. So when the voltage is negative, the current slope is falling. So it will be like this. Like this, where this is delta IL2, this is delta IL2, and it has some average value. This where this is IL2. So this waveform is IL2. Now we'll draw the waveform of the switch 1, IS1. So when switch is on, IS1 is what we have written here. IS1 is IL1 minus IL2. So we'll do, for the both the waveforms, we'll do the summation. IL1 minus IL2. So minus IL2 means the waveform is mirror image in the other direction. So IL2 is negative. So here if you see the waveform of IL2 is, so it's a falling slope. So we can write y is equals to minus mx plus c. So if you multiply by negative sign, y equals to mx minus c. Y equals to minus mx plus c. So y equals to mx minus c. So the intercept becomes negative and the slope becomes positive. So minus IL1 is like this. We'll draw a waveform, a dummy waveform of minus IL1. The intercept is negative and the slope is positive. So it will be like this. The negative value of IL. So this is minus IL2. This is the waveform of minus IL2. And the waveform of IL1 is like this. Like this. This is the waveform of IL1 and this is the waveform of minus IL2. You just have to add both the waveforms. So this has one slope and this has one slope. Assuming that the slope is a function of inductor, here it is L1 and here it is L2. So it gives some other slope. So let's assume that the slope is adding up like this. Like this. So this is the waveform of IS1. This is how IS1 will look. So VS1 is done. IS1 is done. So yeah, inductor is done, switch is done. Now the capacitor. Now the capacitor. First we'll draw the waveform of the capacitor current and then we will establish ICC dV by dt. Then we'll integrate the waveform to get the voltage of it. Okay, so first we'll see what is IC1. In the first case when the switch is on, IC1 equals to what is IL2, and in this case what is IC1? IC1 is IL1. Okay, so it's clearly visible, seen from this waveform that in first case IC1 is IL2 and in second case IC1 is IL1. So nothing, we just have to draw the waveform. So we'll quickly draw the waveform of these things. I think now I'll erase these waveforms. First is current, so current will draw in this color. First is during on time. IC1 is IL2. First we'll draw the waveform of IL2. So we'll use this color. Yeah. So when the switch is on, current is IL2. This is IL2 in blue color. We'll draw only these stuff. And the switch is on, it is this. The switch is on, it is IL1. So IL1 is this during the off time. So it is like this. Like this. We assume that the slopes are not same. So like this, it is somewhat like this. This is something different and this is something different. So this is IL2 and this is IL1, and this waveform is IC1. So IC is C dV by dt. So V is 1 by C integral dt. So we have to do the integration. So integration of a ramp signal is what? Quadratic signal. So here the ramp is falling. So here quadratic signal should fall. So the voltage waveform is like this, somewhat like this. Almost constant, because we are assuming that the capacitance is such a big that it will take care of this ripple. This waveform is VC1. So it has some ripple content of delta VC1 like this. So VC1 IC1 is done. So we have to run the waveform of the inductor also. Then the remaining thing is diode and the output. The last ones are diode and the output capacitor. Then comes the diode. When the switch is on, what is VD1? If we apply a KVL here, then VL2 is VD1 plus V0, or VD1 is VL2 minus V0. But what is VL2? VL2 is minus VC1. So it is minus VC1 minus V0. So the voltage across the diode is negative. So that's why it is reverse bias. Yes, minus VC1 minus V0. So it is negative. We'll assume that it's almost constant, minus VC1 minus V0, because here, as I have shown you, key waveform of VC1, the capacitor C1 and C2 are big, that it's almost a constant waveform, which we can write here. So here you can write minus VC1 minus V0. And in this other case, the voltage across diode is 0. This is VD1. Now we'll draw ID1. ID1. First case ID1 is 0. So we'll draw the 0 ones. And in the second case, what is ID1? So yeah, IL1 is equals to IL2 plus ID1. IL1 equals to IL2 plus ID1. So ID1 is IL1 minus IL2. When it is off, which is similar to IL1 minus IL2 in the positive direction. So this is IL1 minus IL2. First see IL1 and IL2 in the negative times. So IL1 is falling, IL2 is like this. So it also has some slope. So it will have a large slope, just like IS1. So this is 0, this is IL1 minus IL2, and this is waveform of ID1. Okay, so this is waveform of ID1. Here you can see that ID1 has some average value and it has some ripples. So using the same principle, using amp second balance, the ripple goes to the capacitor and the average value goes to the load, because the load is constant. So let's say that this is the average value. capital I D1. So if we just draw the waveform of the capacitor current, it will be this ripple. A waveform with a big slope, because the waveforms IL1 and minus IL2 are added. So this waveform should have zero average value. This is the waveform of IC2. So the value by which it goes down is, this value is ID1, its average value. IC2. This is IC2. And what will be BC2? Integration of this. Integration of constant. There is a ramp signal, so it will be like this. Then it will be like this. Somewhat like this. Then again ramp. A falling polynomial. Ramp. Falling polynomial. This waveform is V0. So V0 has some delta V0, which is delta V0. This is waveform V0. So we have drawn all the waveforms of it. So if we quickly do the volt second balance, first is of volt second balance of L1, because just like similarly we have A1 A2, we should have A3 A4, which is this is A3 and this is A4. So A1 equals to A2 and A3 equals to A4. So Vin into T switching equals to Vin minus Vcn minus V0 into this. So it will be this will be what? VL1 during on into D into T switching plus VL2 during off into 1 minus T into T switching should be equals to 0. What is VL1 on and VL1 on is Vin. So Vin into T. So T switching gets cancelled. V into D plus VL2 off. What is VL2 off? Vin minus VC1 minus V0. Plus Vin minus VC1 minus V0 into 1 minus T equals to 0. So what we got is dVin equals to VC1 plus V0 minus Vin into 1 minus T. If you bring Vin to this side, it will be minus becomes plus. So D minus T becomes 0, so it will be Vin. So Vin equals to 1 minus T times of VC1 plus V0. This is equation number 1. So we have to get the ratio between Vin and V0. So we have to get rid of VC1. We'll get rid of VC1 by doing volt second balance of L2. So volt second balance of L2 is VL2 on into T into T switching plus VL2 during off into 1 minus T into T switching will be 0. So what is VL2 on? Minus VC1 and V0. So it is minus VC1 into T plus V naught into 1 minus t equals to 0. So t into Vc1 equals to V naught into 1 minus t, or Vc1 is what? V naught into 1 minus t by t. So using 1 and 2, what we'll get, we'll substitute value of Vc1 in this expression, then we'll get V in is 1 minus t times of V naught plus Vc1, which is V naught into 1 minus t by t. So if we take V naught common, it is V naught into 1 minus t into 1 plus 1 minus t by t, which becomes V naught into 1 minus t, numerator, denominator it will be d, so it will be d plus 1 minus t, so it will be numerator, it will be 1. So therefore V in equals to V naught into 1 minus t by d, which means that V naught is V in, or V naught by V in equals to d by 1 minus t. So it's a buck-boost derived converter. So SEPIC converter is a buck-boost derived converter. Now to find the minimum load, so it's a buck-boost derived, means ultimately it's a boost derived. When if d is between 0 to 0.5, it acts as a buck, and from 0.5 to 1 it acts as a boost. So ultimately if d is in that range of 0.5 to 1, then it acts as a boost converter, which means that we should find the minimum the minimum load across it. So for finding the minimum load across it, we have to see the discontinuity of the waveform. But now which waveform to consider? So here this is the diode current ID1. This is ID1. So the point at which the waveform ID1 so before this we'll also do the amp second balance. So amp second balance, first is amp second balance for C1. What is amp second balance? IC1 during on, no, the average value, because it happens only on average value. So where is the waveform of I7? Yeah, this one. Yeah, so IC1 during on, actually writing average value is wrong actually, so we'll write like this: IC1 during on into D into T switching plus IC1 into off into 1 minus T into T switching becomes 0. What is IC1 during on and IC1 during off? It is IL2 and IL1. So now we'll replace it with their average values. So IL2, it will be IL2 into T plus IL1 into 1 minus T equals to 0. The relation will be IL1 equals to minus D by 1 minus T into IL2. So this is some equation number 3. Here it means that average value of one current is negative with respect to each other, which means that here what happened is, our assumption was this was the positive direction of IL2 and this was the positive direction of IL1. It means that whatever is our convention, either one of them should be reversed, which means that if say this is the dot convention, here dot doesn't mean the transfer, I am just saying dot means the current entering. If our dot was here and here, so and if we do all the analysis here, so ultimately we'll get that the ratio between average values of L1 and L2 is negative, which means that either one of them should be negative, which means that this dot, instead of placing it here, we could have placed it here. and we could have considered this as the positive direction of IL2. Thus, this should be the positive direction of VL2. This is plus and this is minus. This is the meaning of this negative sign. Okay. Anyways, we'll follow only one convention and then accordingly do everything with respect to it. So second is C2 or C0. So I C2 on into D and directly write D. Okay, D into T switching plus I C2 off into 1 minus T into T switching becomes 0. So what is IC2 on and IC2 off? So this is what? This is minus ID1. And what is this? IL1 minus IL2. But this is the IL1 minus IL2, which is shifted down by the value of minus ID1. So it is minus ID1 into D plus it is IL1 minus IL2. IL1 minus IL2 minus of ID1 into 1 minus T equals to 0. Now what is ID1? ID1 is the load current. ID1 is I load. ID1 is I load. So therefore it will be I load into D equals to IL1 minus IL2 minus I load into 1 minus T, or I load is what? IL1 minus IL2 into 1 minus T. Because this IL2 will be added here, DD will be cancelled, it will be 1. So this is equation number 4. So we can express I load as a function of IL1 and IL2 as well. So using 3 and 4, what we can write is, we substitute 3 in 4. So I load is what? IL1, that is minus D by 1 minus T, minus 1 into 1 minus T into IL2. I'll take IL2 common. So it will be, I'll write minus 1 minus T IL2 into D by 1 minus T plus 1, which will be 1 minus T will be cancelled, so it will be minus IL2 into D plus 1 minus D, which is 1. So here it is I load. So this is what we got. I load is minus IL2. Again, there is a negative sign here, which means that we have to reverse the convention of IL2. If I load is minus IL2, what is IL1? Using equation number 3, IL1 is minus D by 1 minus T into IL2. IL2 is minus I load. So it will be D by 1 minus T into I load. Now what is IL1? IL1 equals to I in, input current, and I load equals to I output current. I load equals to I out. So if we neglect the losses, what we can write is P in equals to P out. P in is V in into average value of I in equals to V out into I out or I load. So here input current is what? I in equals to IL1 and I out equals to I load. So therefore To verify this relation, we will verify using this identity. V in into IL1 equals to V naught. What is V naught? V naught is V in into d by 1 minus t. So V in into d by 1 minus t into I load. If V in gets cancelled, what is IL1? IL1 is d by 1 minus t into I load. This matches with this, which means that our analysis of current second balance or amp second balance is correct. This is how you should verify volt second balance and amp second balance using each other. So first do volt second balance, then do amp second balance, and then verify amp second balance with volt second balance using power balance, that is P in equals to P naught, by neglecting all type of losses, that is no equivalent series resistance of L1 and L2, and also for C1 and C2. Now quickly we'll see the critical inductances. Critical inductances for SEPIC converter. First is L1. So yeah, similar analysis we can do. Just touch this waveform to this. So we'll do a generic analysis and then we'll make it more narrow. So this waveform is pushed down, so it becomes like this. So this is IL max, this is ILI, this is ILI, where I equals to 1 or 2, first inductor or the second inductor. This point is ILI max, this point is ILI min, and this is delta IL. This is delta ILI. So first we let ILI minimum. So ILI minimum is what? ILI minus delta ILI by 2. So IL minimum becomes 0 for critical conduction mode. For critical conduction, that is when the waveform is just on the verge of going into DCM, discontinuous conduction mode. So therefore IL of I equals to delta IL of I divided by 2. So first we'll do for L1. For L1, IL1 equals to delta IL1 by 2. And what is delta IL? VL is L delta IL by delta T, which means that delta IL is VL into delta T by L. This we have to put L. Yeah. So IL1 equals to delta IL1, that is VL by 2L. So we'll write during on time. So during on time, what is VL on? That is V in. So here we'll write, instead of VL, we'll write VL on, into delta T we'll write T on, that is D into T switching or D by F switching. So, and VL on is V in. So it is V in D by 2 L F switching. That is IL1. And we'll write IL1 in terms of load. So IL1. What is IL1? D by 1 minus D into I load. D by 1 minus D into I load. So here L equals to L critical. So therefore now we'll find the value expression of L. So L critical equals to what? Here the dd will get cancelled, nothing else will be. L is In the numerator it will be Vin into 1 minus t by 2L into I load. L will be V into 1 minus t by 2 L nahi, L won't be here, L will go there, V into 1 minus t by 2 F switching I load, yeah, 2 F switching in I load is V naught by R, so it is V naught into 1 minus t divided by 2 F switching, I load is V naught by R. Then V naught also we can write it in terms of V in, that is V in into 1 minus t into R by 2 F switching into V naught is d by 1 minus t into V in, because it is buck boost ref converter. So V in will cancel, so it will be R into 1 minus t whole square by 2d into F switching. Therefore L1 critical is this, R into 1 minus t whole square by 2d into F switching. This is for the first inductor L1. For L2, similarly, IL2 is delta IL2 by 2, that is, here we'll let VL1 on is VL2 on into D by 2 L2C. Here we will let L1 is L1C, yeah, VL2 on into D by 2, yeah, into F switching. What is VL2 on? VL2 on is minus VC1, or we can write in terms of V naught. So instead of writing in terms, because it is minus, so let's write in terms of plus. So let's erase this. So we'll write this as delta L2 is what? Yeah, VL2 off into T off is 1 minus T by F switching. So 2 into L2 into F switching, where L2 is L2C. And VL2 off is V naught. Yeah, it is V naught. So it is V naught into 1 minus T by 2 L2C into F switching. This is IL2. And what is IL2? IL2 is I load. And I load is V naught by R. So therefore V naught by R equals to V naught into 1 minus T by 2 L2 critical into F switching. So this will get cancelled. So therefore L2 critical will be R into 1 minus T by 2 F switching. This is the L2 requirement. Okay, so we'll quickly see how to find the capacitances. Design of capacitances C1 and C0. So just like this analysis where we have seen design of parameters for DC-DC converters for buck boost and buck boost converter, what we found was L2, while selecting any inductor, L should be greater than L critical and for a given ripple rating. So before this, let's quickly write. So you know that generic approach for inductor selection of selecting L1, L2. So we know that VL is L delta IL by delta T. So it means that L is VL delta T by delta IL. Yeah. So we'll split the analysis into two parts. First is for L1, second is for L2. So L1 is, we'll write VL1 on into T on is D by F switching into delta IL. And what is VL on? VL1 on, VL1 is V in. So this is V in. So L1 is V in into D by F switching into delta IL. But delta IL1, sorry. VL1, L1, delta T. Okay, means generic approach we are writing L1. And L2 is what? L2 equals to VL2 off into 1 minus D by F switching into delta IL2. It will be 1. VL2 off is V0 and this is V in. So therefore L2 is V0 into 1 minus D divided by F switching into delta IL2, where delta IL1 is some X percentage of IL1, which is given X1 percentage of IL1, and similarly delta IL2 is some X2 percentage of IL2, which is also given. So how to choose L2? L2 is maximum of not L2. L1 is maximum of L1 critical comma V in D by F switching into what? Delta IL1. This is how you select L1. L2 is similarly maximum of L2 critical comma V0 into 1 minus D by F switching into delta IL2. Where, as I said, delta IL1 is X by 100 into IL1, that is 0.0x IL1, and delta IL2 X1 percentage is X2 by 100, that is some percentage of IL2 which is given to us, 4%, 5%. So like that 0.0x2 into IL2. So this we can select. Now the design of capacitors is by seeing the waveform. Waveform of the capacitor current. Now here IL2 and IL1 is there. So as per our analysis, the waveform of IL2 should be reversed. Means a negative sign should be applied to it. This was based on our analysis. Yeah. So the area of the waveforms IL1 and IL2. So A1, A2, A3, A4 is done. We'll have to see. Here I will write this is some A5. This is A6. And this is A7, A8. So first C1, we know that ICC dvc by dt, or C delta vc by delta t. So we'll write C as IC delta t by delta vc. Or this we can write as IC dt by delta vc. Means instead of doing this all things, let us simply write dvc is C into dvc is IC dt. So let's integrate it on the both the sides. So C integral dvc is integral IC dt. So this depends on the time interval, for how much time interval we want to integrate it, because as the average value of capacitor current is 0, which means that the areas are equal, positive and negative areas both. Here, as I told you, that the area for A5 and A6, that is for the capacitor current C1 IC1, the both are positive areas. It is because our convention of choice of IL2 has been reversed. So IL2 has to be negative, then only the area will come down. So that's why, that is the reason why this will be there. So anyways, even if both the areas are positive, we'll get a negative sign there. So which means that again, if we redo the analysis by considering or reversing the direction of IL2, everything will go correct. So that is not the worry. So here only IL2 direction we have to reverse because it is negative. So for C1, we'll do the area. So basically here it is, let's say that we are integrating it for the half time period, 0 to t switching by 2. So here also it is 0 to, not t switching by 2, 0 to t on, that is d into t switching, d into t switching. Also it is 0 to d into t switching. What is the average value of capacitor voltage in on time for C1? So we have to see VC1. Where is VC1? VC1. What is VC1 during the on time? VC1 is minus VL2. Yeah. So during the on time, the average value of the capacitor voltage is VC1, and VC1 is minus VL2. So let's write here minus VL2. But what is the average value? Average value of any term, let's say it is x, is 1 by t integral 0 to t x of t dt. This is the average value, and this is the average value. So what will write? Integral 0 to t x of t dt is what? T into average value of x. This we can write 0 to t like this. So this is here, also this is here. What is this? Okay, so yeah, this is this. So basically integral this we can write as t into this. What is t? T is the limit till which we are integrating. Here t is d into t switching. So the value of, therefore, integral dvc from 0 to d into t switching is what? T, which is d into t switching or d by f switching into average value of x. What is the average value of the capacitor current in half time? We have already written here. It is what? VC1 equals to minus VL2. VC1 is minus VL2. We'll write minus VL2. So let's write everything in terms of V and V0, not VL2. So here during the volt second balance, we have written, the expression of V0 by V as d by 1 minus d. So we'll quickly write the value of Vc1. Vc1 in terms of V and V2 from this expression. So V in is 1 minus d. So we'll write here V in will bring 1 minus d down in the expression of equation 1. V in by 1 minus d is equals to Vc1 plus V0. So minus V0 is Vc1 with this. So it is V in by 1 minus d, and V0 is what? V0 is minus d into V in by 1 minus d is Vc1. So denominator is common. So 1 minus d into V in is Vc1. So average value of Vc1 is V in. So average value of Vc1 is directly V in. Directly we have to write Vc1 as V in. So let's write here IC1 C1 dVc1 C1 dVc1 IC1. So dVc1 VL, here we have written minus VL2. So average value of X is what? Vc1 where Vc1 is V in. So it is D into V in by F switching. This is the value of this term. So therefore what is LHS? LHS is C1 into D into V in by F switching. And what is RHS? RHS is integral 0 to D into T switching into IC1 into dt. Now if we just quickly draw the waveform of IC1 in the on time only, it will be what? It will be IL2 like this. Like this. This will be IL2. This is D into T switching. If this is IL2, this is IL2 minimum. And this is the whole area AM. Let's write this area as AM. So what is this? This is the area AM. Area AM. What is the area? Area AM is area of the rectangle plus area of the triangle. What is the area of rectangle? Area of rectangle is length into breadth. Length is D into T switching or D by F switching into height. This height is IL2 minimum. So IL2 minimum, this plus area of triangle is half into base, that is D by F switching into half into base into height. Height is what? IL2 max minus IL2 minimum. So this is what? Delta IL2 into delta IL2. And what is IL2 minimum? IL2 minimum is, this is capital IL2 minus delta IL2 by 2. So therefore AM is D by F switching into IL2 minus delta IL2 by 2 plus D by 2 F switching delta IL2. If you see, this term and this term are same. So it is D IL2 by F switching. So therefore equating LHS and RHS is C1 into D into V in by F switching equals to D IL2 by F switching. So actually here there is something missing. RHS is integral of 0 into D, integral 0 to D T switching into IC dt. which is area, which I have said that it is area by M, but actually it should be area by T into the time, that is D into T switching. So into D by F switching, this will get cancelled, so it will be IL2. So if we erase this, it will be IL2. So therefore C1 is IL2 F switching by D into V in, or iload is V0 by R, V0 F switching by R D V in, or again we can simplify it V0 as D into V in into F switching by 1 minus T into R into D into V in. D V in gets cancelled with D V in, so it is F switching by 1 minus T into R. Therefore C1 is F switching by 1 minus T into R. Similarly, quickly we'll see analysis for C2. So again the same thing, integral what it was, C1, yeah, C2 integral dVC2 VC2, where we are integrating, because the analysis for positive half cycle is easy, so D0 into D into T switching equals to integral IC2 dt, IC2 dt from 0 to D into T switching. So again similarly LHS is what, C2 into time into average value of the voltage term. Time is what, D T switching or D by F switching into average value of VC2 during on time. What is VC2 during on time? That we have to see. VC2 during on time is V0 only. VC2 is always V0. So VC2 is V0 equals to 1 by T or 1 by D T switching or F switching by D into area under IC2 graph. So here area is this. For positive it's like this, area is this. So this value is I load and this is T on. T on is 1 minus D into T switching. So yeah, sorry, D into T switching. So D by F switching into I load. I load is V0 by R. This gets cancelled. So and V0 gets cancelled. So therefore C2 is F switching by DR. So again using the similar analysis for the ripple, ICC delta V by delta T. So C is IC delta T by delta V. So delta V is some X percentage of average value of VC. Like this we can express some percentage of it. And ICDT is what? Is area under the IC versus time graph. So using this analysis also you can find the capacitance. So the last analysis that we'll do for the SEPIC rotor is the minimum load. Minimum load calculation for the boost mode of operation. That is when 0.5 is less than t is less than 1. So how to find the minimum load? Now there are two inductances. So to find, so here using the second balance, what we found that IL2 equals to ILoad. IL2 equals to ILoad. So we have to see the inductor whose average value can be rated directly to the load current. That is, whatever is the average value of this inductor current, it goes to the load. Negative sign means that the convention of current is reversed. So it means that to see with respect to the load perspective, we have to consider the analysis of L2 instead of L1 for finding the minimum load. And for finding the minimum load, we have to do the similar analysis. The analysis is that we have to find L2 critical. So in the expression of L2 critical, it is rated in terms of R. So we have to express R in terms of the other terms. So L2 critical was this. This will copy. So first we'll write that since IL2 equals to minus ILoad, L2 critical conduction mode should be considered for calculating R minimum. That is, we have to do this. So here R equals to R minimum and L2C equals to L2. So therefore, what is R minimum? R minimum is 2L2 F switching by 1 minus D. R minimum is 2L2 F switching by 1 minus D. So this is how we calculate the minimum load on the SEPIC converter if it operates in the boost mode. Nothing. The calculation, the basic concept behind finding minimum load for any boost or boost derived converter is nothing but seeing the amp second balance of the inductor which is placed towards the load, and whatever is the principle that we use for calculation of the critical inductance, that is when the inductance waveform just touches the zero axis, the same principle is used for finding the minimum load. So the expression of R minimum and L critical is same only. Just the thing is that in the expression of L critical we write R, only R, and L as L critical. The same expression, if we remodify and redo it, we find R in terms of L, and in that case R is R minimum and L is the normal inductance, not the critical inductance. So both are same expression because both are derived using the same principle, that I minimum is 0, that is when the waveform is just on the verge of going discontinuous. It is just the way in which we are expressing the waveform. If we write the this expression in terms of L, it is L critical. If we express it in terms of R, it is R minimum. So both are the same thing. Now if it is a higher order converter, which inductance should we consider for R minimum calculation? It is the inductance which is placed close to the load or whose average value can be directly rated to the load. In this case IL2 was minus ILoad or ILoad. That's why we have considered L2 critical. Otherwise we should have considered L1 critical. So in this lecture we started with the analysis of SEPIC converter, the circuit diagram, its equivalent circuit in the on time and off time of the switches. Then we coded the states with each other. Then we started with the steady state analysis of the SEPIC converter. We have drawn all the waveforms. Then volt second balance of both the inductances. We established the relation between V0 and Vin. Then VC1 and Vin here, V0 and Vin here. So this is M of T, the steady state voltage gain of a SEPIC converter. Then amp second balance, we derived the relation between ILoad, IL1 and IL2, and we verified the amp second balance with the power balance by assuming no losses. Then we analyzed the critical inductance for L1 and L2. The selection of L L1 and L2 in terms of critical inductance and in terms of a given percentage ripple in the inductor current. Then we went to the design of capacitance C1 and C2 by using the integral approach, and we also have seen how to select the capacitor based on a given percentage ripple, which is here x% of Vc, and this is area under IC versus time graph. Then we found what is the minimum load required for a SEPIC converter operating in a boost mode, which is very similar to the critical conduction mode of operation. But which inductor to consider? The inductor which is placed close to the load, that inductor we should consider, and using the expression of L critical we'll find the R minimum for the SEPIC converter. So in the next lecture we'll see the analysis of the chuck converter. Thank you.